Europe's biggest volcano just slid 4 centimeters in 8 days. And scientists are not talking about the eruptions. They are not talking about the lava. They are talking about something far slower, far quieter, and potentially far more devastating. The entire eastern flank of Mount Etna is racing toward the sea. Not in a million years, right now. And the latest data from 2026 has just revealed a hidden connection that changes everything we thought we understood about this mountain. A connection deep beneath the ocean floor that could turn a slow geological slide into a catastrophic wall of water crossing the entire Mediterranean. The catastrophic potential is clear. 1 million people live on the slopes of this volcano. Millions more line the coasts surrounding it. And here's the part that has researchers genuinely alarmed. This has already happened before, once. 8,000 years ago. The evidence is still buried in the seafloor. So the question is not whether Mount Etna's flank can collapse. We know it can. The question is, are we already watching it happen in slow motion right now? In April 2016, a team of scientists from the Helmholtz Center for Ocean Research in Kiel, Germany, launched a bold and unprecedented experiment in the waters off Sicily. Their focus was Mount Etna, one of the most active volcanoes on Earth. Specifically, they targeted the unstable eastern flank of the volcano, a massive section of rock long suspected of slowly sliding toward the Ionian Sea. For decades, researchers debated what was driving this motion. Was it magma pressure building beneath the surface, or something else entirely? To find answers, the team deployed 5 acoustic transponders onto the floor of the Ionian Sea. These instruments were carefully positioned above the submarine extension of the fault line separating Etna's unstable flank from its more stable western structure. This marked the first time long-term geodetic monitoring equipment had ever been installed on the seafloor in this region. For the first time, scientists would be able to measure, in real time, whether the base of the volcano was moving beneath the ocean. The mission ran for more than a year, collecting continuous data through July 2017. When researchers analyzed the results, they discovered something extraordinary. During a single 8-day period in May 2017, the seafloor had shifted 4 centimeters. At first glance, 4 centimeters sounds insignificant. But what moved was not a small rock formation. It was an entire volcanic flank, hundreds of cubic kilometers of solid rock. A geological structure that had taken roughly 500,000 years to build shifted as a single mass by 4 centimeters in just 8 days. In geological terms, that is an enormous and deeply unsettling movement. Yet the most groundbreaking revelation was not the amount of displacement, but its pattern. The greatest movement occurred near the coastline, while the least occurred near the summit. This directly contradicted the long-standing theory that magma pressure was forcing the flank outward. If magma were responsible, the summit region should have shown the strongest motion. It did not. This single observation overturned decades of scientific assumption. The data revealed that magma was not the primary driver. Instead, gravity was in control. The southeastern flank of Mount Etna is being pulled steadily seaward by its own immense weight, sliding over soft clay sediments beneath it. The mountain is not being pushed from below. It is slowly, inexorably collapsing toward the sea. Most people think about Mount Etna as a problem that exists above the ground. Lava flows, ash clouds, eruptions visible from space. But in January 2026, a study published in Science Direct forced researchers to look in an entirely different direction. Not up at the volcano. Down. Into the ocean floor beneath it. The study integrated geological, geochemical, geodetic, and archaeological data collected from Etna's eastern flank over multiple decades. And it reached a conclusion that substantially changes the way scientists understand this entire system. The sliding faults responsible for the flank's instability are not operating in isolation. They are directly connected to the hydrothermal vents on the floor of the Ionian Sea. Here is how that connection works.
As Mount Etna's southeastern flank slowly slides, it fractures the rock beneath, creating pathways for hot, mineral-rich fluids that feed an entire underwater hydrothermal ecosystem. Scientists describe this relationship as coupled. Tectonic instability and hydrothermal activity depend on each other, meaning any acceleration in sliding could disrupt the system in unpredictable ways. Etna sits on the edge of the geologically active Calabrian subduction zone, with surrounding Ionian Sea faults moving independently and posing hazards as serious as the volcano itself. On January 1, 2026, a flank eruption began inside the horseshoe-shaped Vallée de Love scar, the most unstable section of the volcano. Lava flowed down the valley, producing ash clouds over eastern Sicily, but no immediate threat to populated areas. The eruption, however, signaled that pressurized magma was accelerating the flank slide. 10 days later, a magnitude 5.3 earthquake struck the Ionian Sea floor independently of Etna, showing that faults beneath the ocean move on their own timeline. Both systems are active simultaneously. 8,000 years ago, the eastern flank collapsed suddenly, generating a tsunami that traveled across the entire Mediterranean to modern-day Israel, proof that these events can happen rapidly and catastrophically. This is documented history, not speculation or alarmism. This is documented evidence, preserved in marine sediments on the seafloor and encoded in the growth rings of ancient trees. For 8,000 years, this record has been waiting in the earth to be deciphered. And what it reveals is simple and unsettling. Mount Etna has already experienced this kind of collapse once. The conditions that triggered it then are still present today, and the southeastern flank continues its slow, inexorable movement.
The scale of what a repeat event would mean in 2026 is almost difficult to process. Approximately 1 million people currently live on the slopes of Mount Etna. Millions more inhabit the coastal communities surrounding the Ionian Sea. The ports, the cities, the tourist infrastructure built along these shores exist with almost no physical buffer between them and open water. A tsunami generated by a significant flank collapse would not offer hours of warning. It would offer minutes. Researcher Marilia Urlaub, who led the Helmholtz Center study, was direct when asked about the risk of sudden acceleration. Her answer was not reassuring, but it was honest. It could happen in 10 years. It could happen in 100. It could happen in 100,000. Science does not currently have the tools to narrow that window with any meaningful precision. That uncertainty is not a reason for dismissal. It is the entire point. The 8,000-year-old tsunami was not predicted either. The communities in its path had no monitoring systems, no warning protocols, and no understanding of what the mountain above them was capable of. The question worth sitting with is a simple one. How different are we, really? Mount Etna is not being ignored. If anything, it is one of the most watched pieces of ground on the planet. Dozens of seismic sensors are embedded across the volcano's slopes. High-precision GPS units track surface movement in real time. Satellites equipped with InSAR imaging technology measure ground deformation from orbit, detecting shifts of just a few millimeters across the entire volcanic structure. And beneath the Ionian Sea, underwater transponders continue the work that the Helmholtz team began in 2016, listening for movement in the fault systems that no surface instrument can reach. All of it runs continuously, 24 hours a day, every day of the year. If the southeastern flank begins to accelerate significantly, the monitoring network is designed to detect it. Mediterranean tsunami warning systems are already in place for coastal communities across the region. The infrastructure of awareness exists. That matters, and it should not be minimized. But the data coming out of 2026 is forcing scientists to confront something that monitoring alone cannot resolve. The connection between the flank sliding, the seismicity of the Ionian Sea, and the submarine hydrothermal vents is far more tightly integrated than researchers understood even 5 years ago. These are not 3 separate problems being tracked by 3 separate teams. They are one system. And the behavior of one component directly influences the stability of the others in ways that current models still cannot fully capture. There is also the question of what accelerating flank movement would mean for the deep sea ecosystems sustained by those hydrothermal vents. Entire communities of organisms exist on the floor of the Ionian Sea, dependent on the mineral-rich fluid discharge that the sliding faults make possible. A significant disruption to that system would not just be a geological event, it would cascade through an ecosystem that exists nowhere else in precisely this form. The honest scientific position, held by the researchers closest to this data, is this: detection is possible, prediction is not. The monitoring systems can tell us when something is changing. They cannot tell us how far that change will go, or how fast, or what threshold separates a measurable acceleration from an irreversible one. The people who live on the slopes of Mount Etna are not unaware of the volcano above them. They have grown up with eruptions. They have watched lava flows creep toward their villages and recede. They have learned to read the mountain's moods in a way that outsiders cannot fully appreciate. But the threat that the 2026 data describes is not the threat they have been preparing for. It is quieter, slower, and it does not announce itself with fire and ash before it becomes catastrophic.
Early warning systems are in place throughout the Mediterranean, far more advanced than they were just 10 years ago. Yet the rapid pace at which a major flank collapse could trigger a tsunami leaves very little time between detection and action. The window is measured in minutes, not hours. Evacuation protocols built for slower-moving disasters don't automatically apply when the threat is already barreling through the water before the alarms even sound.
The January 2026 eruption and the magnitude 5.3 earthquake that followed 10 days later were not catastrophic events in isolation, but their proximity in time matters. Two separate components of the same interconnected system activated within days of each other. Researchers flagged the coming months as a critical observation window precisely because of that sequence. Not because disaster is imminent, because the system is demonstrably awake. The broader implication extends well beyond Sicily. Mount Etna is not a regional curiosity. It is a window into how volcanic, tectonic, and oceanic systems behave when they are stressed simultaneously. The lessons being learned here about coupled geological systems, about the limits of predictive modeling, and about the gap between monitoring capability and true forecast precision apply to volcanic coastal environments across the entire planet. What scientists want the public to understand is not that catastrophe is coming tomorrow. It is that awareness is not the same as alarmism. Understanding the real nature of this threat, its scale, its interconnections, and its historical precedent is the only foundation on which meaningful preparedness can be built. The mountain is not waiting for the conversation to catch up. It is already moving. The people who live on the slopes of Mount Etna are not unaware of the volcano above them. They have grown up with eruptions. They have watched lava flows creep toward their villages, sometimes slow enough to film, sometimes fast enough to redraw maps. They have swept ash from balconies, listened to windows rattle in the night, and returned to daily life once the smoke thinned. Over generations, they have learned to read the mountain's moods in ways satellites and sensors still struggle to replicate. But the threat described in the 2026 data is not the kind that glows red against the sky. It is not a spectacle of fountains and fire. It is quieter, slower, and far more structural. And it does not announce itself with drama before it becomes catastrophic. Across the Mediterranean, early warning systems are more advanced than at any point in history. Seismic networks triangulate tremors in seconds. GPS stations measure ground deformation down to millimeters. Ocean buoys register subtle shifts in sea level. Yet even with this technological web in place, a significant flank collapse presents a brutal timing problem. The physics are unforgiving. If a massive section of Etna's unstable eastern flank were to slide into the Ionian Sea, the displacement of water could generate a tsunami within minutes. Minutes are not hours. Detection is not evacuation. Emergency frameworks designed for lava flows or ashfall assume time. Time to analyze. Time to decide. Time to move. A landslide-triggered wave compresses that timeline into a narrow and unforgiving window where hesitation becomes consequence. The January 2026 eruption, followed 10 days later by a magnitude 5.3 earthquake, did not devastate Sicily. In isolation, neither event qualifies as extraordinary for a volcano as active as Etna. But proximity matters in geology. Two components of a deeply interconnected system activated in rapid succession. Magma movement alters internal pressures. Seismic shifts redistribute stress along faults and within the volcanic edifice itself. Researchers identified the months following that sequence as a critical observation period, not because disaster is inevitable, but because the system demonstrated coherence. It moved as one organism rather than isolated parts. It signaled wakefulness. What unfolds on Etna's slopes is not solely Sicily's concern. Mount Etna is one of the most instrumented volcanoes on Earth, precisely because it serves as a living laboratory.
The interplay between volcanic activity, tectonic stress, and the ocean floor provides rare insight into connected geological systems, lessons that apply to coastal volcanoes worldwide. Monitoring and modeling have improved, but precise forecasting remains impossible. Scientists are not predicting an imminent apocalypse. They are stressing a crucial distinction. Awareness is not alarmism. Understanding structural vulnerability matters more than panic. Mount Etna is already moving 4 centimeters in just 8 days. Beneath its slopes lies 500,000 years of volcanic rock sliding over soft clay, above active faults and hydrothermal vents supporting deep-sea ecosystems. This system has already produced prehistoric tsunamis, eruptions, and earthquakes, all documented and connected. The January 2026 eruption and subsequent magnitude 5.3 earthquake show the system is active, coupled, and ongoing. Mount Etna has moved long before humans settled its slopes, and it will continue moving regardless of our understanding. Monitoring is active, data is being collected, and warnings are issued. But the question remains, is anyone paying attention?